Okay, guys, work on the example. Yay, you did. Okay, so here we go.
Hello.
You gonna start singing? Bust out some Adele. All right, so
Nikki G.
Yellow.
how do we do? Okay, done. I say hi back. There's only so many hellos you really need. Unless the person's not listening, then what's the point, right? Anyway, still music. So, coming on back, how do you multiply a vector by a constant? John, you were answering. Go.
Oh, I was just taking its form, like the places form.
Uh-oh. What's that called? What's this form when there's little side carrots?
Component form.
Component form. If you want, you can make it like a little alien or something. That's some more tennis. Anyway, but that's not it. It's called component form. So, how do we multiply a vector by a constant k? You multiply each of, what are these called? Each of the vectors. Louder. Components! Thanks. That was delayed. Anyway, how do we multiply a vector by a constant? We multiply each of its, everybody.
Components.
Components, because what is this form called with the side carrots?
Component
Component form. How do we add two vectors? Vector addition.
It's because
You place the tails and stuff.
Sometimes you kick.
In a graph, we'll get to that, but in the actual just easy algebra of it, or math of it, how do we add two two vectors in component form? Add the horizontal components and add the vertical components. Oh, sorry, my screen kind of cut off. Add the horizontal components and add the vertical components. It's as easy as that. Combine like terms, basically. Combine like terms, basically. So when you guys got to your example today, we'll come back to the picture. Just hang in there. Remember, on this page, the first thing was not the pictures. The first things were the math. Were the math? Was the math. Sorry. Grammar is a little rough today. But even math teachers should be grammatically correct, right? For each. All right, so, well, he wasn't almost an English teacher. Anyway, question. How do we do U plus V? Wait a minute, when you guys wrote this, hold on, wait, did you write it correctly? You gotta write the vector form. You cannot write in bold. So what else should you have written? Shouldn't you have written it there?
Oh, yeah.
Shouldn't you have also written it here?
Yeah.
Little slackers. All right, so coming back. Yeah, I like the one with letters. Otherwise, this is Ray and geometry. And this, like, that's how they do
I think you were totally right.
it. Right? I agree. Wait, hold on. All right, focus on it. We're recording. I have evidence. Question. What's the component form of U plus V?
3 plus 3, 4.
Yeah, right? Doesn't that make sense?
Yeah.
Add the horizontal, add the vertical. Yes, it really is that easy. When you go to do the difference, and does it behave any differently?
No, you just do it again.
No, because 2 minus 1 is 1 minus 3 is. Do you have the components? That's not bad, right? Number next one. What do we do as soon as we have these things called scalars? Wait, scalars. Scalar is a snazzy physics term for a dimensionless quantity. What? A quantity that doesn't have to do with changing direction. Unless it's a negative. Anyway. Scalar, just take it. It's a coefficient, okay? For our mathematical purposes, just say it's a coefficient. 2u minus 3v. Question, how do we get 2u, first of all? Yeah, double the u, and what would that be? And then we subtract 3 times v, and what is that? Does that make sense? Then we gotta put those together, and it's just simply a subtraction. So we end up with 4 minus 3 is 1, 2 minus 9 is? Careful. 1 vector minus another. We could think of it as 1 vector plus a negative times, and if you remember, doesn't a negative distribute, so both of the components are negative? Does that make sense? the 9 negative kind of got lost. Subtraction is addition of the negative. The negative would, like scalar multiplication, go into each of the components, flip each of the components, and we would end up with a quick addition of 4 minus 3 is 1. 2 minus 9 is negative 7. How we doing, guys?
Good.
All right, now, that was supposed to be the easy part. Why am I saying that? Because the bottom says sketch. Now, once again, the math is easy, true? Well, that's not the answer. Oops. The math is easy, right? Now, you might ask, then why on earth do we look at the graphs? And my answer is because of physics. Now, can you guys tell where each of the little vectors from down below came from? What were we given in the beginning? U, which said go over 2 and up 1, right? And then what else were we given? V. And V said go over 1 and up 3. True? Okay. So that's where each of those little vectors in the bottom came from. The first 2 vectors that we had. Can you guys tell why I'm putting the arrows where I'm putting them? Because you start at 0, 0, you go over to the right 2 and up 1. That's why I put the arrow in that direction, because we're headed, what, northeast? At a lower angle. And the other one up, sorry, to the right 1 and up 3 would be northeast at a higher angle. Anyway, so how do we show what we just did mathematically, the U plus V? Let's just start with the first one. How do we show mathematically U plus V on a graph?
You go from.
Do we just connect them and say, yay?
No.
No. Remember yesterday, right now, these are acting on a single object right here. That's one way of thinking about it. But the problem is, have we put these 2 together to see the combined effect? No, they are 2 separate individual vectors working differently on one object. In order to do vector addition, we have to say, no, we need to translate one of the vectors. And actually, let me make it blue just so that you guys can tell. I'm just taking the U vector and saying, let's try to make it actually accurate. Is that roughly parallel?
Yeah.
Roughly, stop judging. Roughly the same length? Yes. Am I allowed to translate a vector keeping the magnitude and keeping the angle, and I can still say that they're equal?
Yes.
Yes, I'm allowed to move them around. I'm allowed to move it around. So I'm taking the original vector, I'm moving it up, and this is what we say in physics, or even just in working with vectors, is orienting the vectors to be head to tail. What do I mean by that? The tail of one connects to the head of the other. So we can see the combined effect altogether. Now wait a minute, tails and heads, what are we talking about? Comets? Kind of. Vectors. Right? Don't comets have heads and tails? You guys are helping. All right.
Sorry.
Who was your science teacher? Physical science teacher. That was probably more elementary. Come back to the very beginning. It's a very good place to be, to start. Remember how we said initial point and terminal point? Can I give you guys another way of talking about them? The tail of a comet, is it behind or is it in front? The tail of the comet is behind. The tail of the dog is behind, right? So we're going to call this initial point the tail. And we're going to call the terminal point the head. Oh, I just said that backwards in the example. This is the correct way. The initial point is the tail, what's behind. The top. The top is the head. Think about it. If you're headed this direction, if you're headed this direction, the tail would be behind. Does that make sense? Like a dog? The tail would be behind. Okay, so hold on. We gotta go back to what I was just talking about with our vector addition in the graphs. Oh, there's a good way. Karina's like, hey, think of it as you're headed this direction. So where the arrow is the head.
Hey!
Goat.
Look at that. I don't know. Okay, so question. Where is the sum? Ready? Wait, hold on. What'd you guys get for the numbers of the sum?
3 and 4.
3 and
It's
4.
gonna be
So we're
right
gonna
there
go over
from
a
origin to
1 and a 2 and a 3, and we're gonna go up a 1 and a 2 and a 3 and a 4. Wait a minute. So this is the sum.
yes.
Ooh, does that make sense?
Yes, ma'am.
Do you see it? 3, 4 were the components. Now I just put the point 3, 4. I just put the point 3, 4. What that stands for is this vector addition. Technically we're headed to the right 3 and then up 4. When we write the vector, we put the little components, but I was just talking about the point itself, where the head is at. But vector addition says take the combined, once again, the combined effect of moving along one vector, moving along the other, and then you can see the combined effect, which is what we call vector addition. Luca, go.
So this is a nice problem because they're both coming from,
Like going the same direction.
yeah, pretty much. If you have one that is like at 3 and 4, and the other one that is like going the totally different way.
Ah, hold on. That's our next
Another
example.
quadrant.
Can we peek at him real fast? Luke is saying maybe this could get harder, and maybe it could. But let's check it real fast. Kiddos, in this second one, this was an illustration of vector u plus vector v, right? That's what this red vector is. Okay, now I need to, in letter B, illustrate what?
Vector u
Minus vector v. Isn't that the same thing as vector u plus negative vector v? That looks like a little underline hyphen something. Hold on. Isn't u minus v the same thing as u plus negative v?
Okay.
Okay. Now hold on. What am I saying? What did we get for the components of u minus v?
1 negative 2.
Wait. Negative 2. Hold on. Isn't this going this way? How on earth do you put those two? Wait. I'm not talking about u and positive v. I'm talking about u and negative v. Let's call negative, or make negative v a different color. That's an awkward color. That's gonna look weird. How about this one? Okay. All right, negative v. We're gonna call him, or make him a different color. Negative v is not on the graph right now. Well, how do I get negative v on the graph? Sean, what do you think?
Well, if it's negative one, that means like, could we just switch points in the magnitude
Mm-hmm.
so that we can make a new one and then use our head to tail rule to get to that point?
Exactly. One way to do it is have this v go the opposite direction. That's one way. Have this v tail to head go the opposite direction. But some of you that looks kind of confusing. An easier way is, kiddos, what are the components of v by itself?
1 and 3.
1 and 3. Then question, if the components of v are 1 and 3, then couldn't I, why isn't it projecting? Couldn't I graph, hold on. Sorry, I've done stuff and it hasn't shown it. It's still not showing anything? Un momento. Por favor.
No, this was
Where are you going with this though?
No, because I was running,
Nothing?
I was like a door, had resisted.
Visualizing is kind of hard. That's it. Let's try again. Am I on the windowy thing? Check. That one gets scary.
Oh, that's me just bugged out. Oh, it came back on.
Struggle. Guys. Oh, we're good, we're good, we're good, we're good.
We all good?
Happy Happy almost birthday. We're back. Okay, so coming back. Wait, hold on. So what would negative v's components be?
Could we multiply them by negative?
Yep, so we'd have -1, -3, right? So where would negative v be on the graph? -1, -3. Does that make sense? Okay, so theoretically we could kind of, in a sense, we could get rid of normal v and say, you know what, you're not really, I mean, you were a factor, he was important and all, but now is he even a part of the equation?
But you see, if you put it back, this, like the angle it forms, like right here, between the light blue and the red,
Uh-huh.
is the same angle as it formed like the blue and the green.
Like if I do this?
Yeah.
Yeah.
They have like the same angle here.
Yeah, because they have to have the same direction, right?
So can I just use that?
You can, but the problem is you're not going to clearly see why that red one is the final answer. Oh, do you mean like moving the blue down?
You got the
red in the top one.
I like it better this way because this way you can see, hey, they're working against each other. They're both working on a single object in the middle, but they're working separately. How do we get them to work together? Can't we shift U down here? And then do you guys see how? Follow the motion. -v plus U is U minus V. One more time. I'm following the motion. -v. Let me undo. So maybe you guys weren't able to follow. I shifted U down, right?
Okay.
And I'm following the motion. -v. -v.
Yeah.
Plus U.
Okay.
Shouldn't that be U minus V?
Yes.
So it technically is in a little bit of a different order in a sense that what we really did was -v plus U, but guys, addition is commutative even with vectors. So these two things are the exact same, and it ends up at the point that you guys found up above, 1, -2. Now, the last one gets a little bit weirder, but hopefully not too much. What are we trying to show graphically? What math? What vector problem? To who? To U minus 3V. Okay, so hold on. I'm going to go ahead and make 2U. Let's make him light green. And let's make -3V purple. Now this time we're going to go ahead and not start with the answer. Let's start with the work. So 2U, we need to take U, which is blue, and multiply him by 2, which only changes his length, right? So instead of going over 2, 2U says, hey, let's go over, oops, wrong color. Let's go over 4 and up what? 1, 2, 3, 4, 1, 2. Undo the 2, should be a little higher. Okay. Here's my 2U. Do you guys see him? He's just double. He's headed the exact same direction. Cool? Okay. Now with my 3V, I need to triple him, which means instead of 1, 3, he's going to be going 3, 9. But it's also negative or subtraction. So instead of going up and to the right or northeast, where's he going to be going? Left and down. So he's going to actually be going 1, 2, 3. And then 9, stink. 1, 2, 3, 4, 5, 6, 7, 8, 9. Struggle. Okay, somewhere down here. That's kind of rough, right? But question, how do I put these two together? Can I translate the little 2U guy down here somewhere? Now hold on, this is approximate. If I had a perfect graph and a protractor and a ruler and I made sure everything was correct, this would be exact. Let's see how close we are. Kiddos, what did we get as the component form of 2U minus 3V? 1, -7. Let's see if it approximately fits. 1, -1, 2, 3, 4, 5, 6, 7. Ooh, not too shabby. Mine did approximately fit. Dun 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 dun.
Dun dun, Steve.
So then can you follow the motion? That was negative 3b, right? Plus 2u. Did we get our vector? Negative 1, 7? Yep. Now, depending on how you graphed, yours might be a little bit more off than mine. I actually wasn't sure how close mine would be. Because look at those little tick marks, they're not exactly evenly spaced, but oh well, I guess the unevenness was even. Anyway, there we go. So kiddos, long story short, for vector addition, can we go ahead and go back and can we add one little note to our little formula of how to do vector addition? I apologize, this is in red, that's kind of annoying. I guess I should have put it black because it's kind of more the formula. In order to add two vectors or similarly subtract just means change the direction or change the components to the opposite sign, right? I do want you guys to know how to easily just put the horizontal and vertical components together. However, I also need you to remember graphically, we have to orient the vectors head to tail. I cannot have two heads together. I cannot have two tails together when I try to do my vector sum. I have to have, if you guys look at the picture down below, I have to go the head of one. Check it. Do you see the yellow line I'm just making? Right there? Okay, now let's go ahead and do it nicely. The head of one, see the head of V? I'm at it right now, a little arrow, has to match up with the tail of U in order to get that correct vector sum at the end. Okay? So one more time. The tail of V has to match up to the, sorry I said it wrong, the head of V has to match up with the tail of U in order to be able to have the correct vector sum. I'll go back to the example. Let me get rid of all those yellow marks. They're kind of masking what's going on. All right. It was a big idea. You guys got it. Let me give a couple more seconds for anybody still trying to get down the example. But we have to move on. Here? Yeah, so it's headed the opposite direction and 3 times as big. Is that right? Then I shifted the 2 down. Okay. Nope, sorry, no. Not it. I was just laying example. Oh no! Life just got interesting. Now wait, pause. Question. I don't know, because look at them, guys.
Oh wait, they look like
A lot of the basic vector operations are what we're used to. Meaning, is addition commutative?
Yes.
Yeah, well that's not too bad, right? So addition is commutative, that's a check. A vector plus 0 is itself. Does that make sense?
Yeah, I guess.
If I did 2 times 3u, wouldn't that be 2 times 3u?
Yeah.
2 times 3u is 6u, and 2 times 3 is 6 times u is 6. Yeah, sure. Whenever they're scalars. Hey, can we distribute a scalar? Yeah. Can we have a scalar on the inside to find the magnitude, or find the magnitude then multiply it by a scalar? Yeah. What's this one called?
Transit.
Almost. Associative?
Nice.
Transitive is the if A equals B and B equals C, then A equals C. Like you translate across kind of. Does u plus negative u equals 0? That makes sense. Can you distribute scalars? That makes sense. 1 times u. Okay, these ones make sense. So I don't really know if you guys need to memorize the ones that make logical sense. It's more important for you guys to memorize the ones that should make sense and don't.
What the property?
Which ones are those?
Not these ones. If you guys want to write down any of them or take a picture of them, you most definitely can. Let me make a picture. If you want to take a picture, you can, but it's not really something I think we need to memorize. Maybe you want a picture just to refer to in case you get stuck on something, but I think you're okay. Anybody else getting a picture? A couple more? Okay, let's keep going now. Okay, unit vectors. We already talked about them, but we have to talk about them more because there are some homework problems. All right, my sillies, focus on it. Anyone watching this video is going to be like, who's talking? It's hard to discern my voice when a lot of you are talking. Apple application. Okay, we've already said unit vectors are vectors with a magnitude of 1, right? The dilemma comes when they ask us to find a unit vector with the same direction as a non-unit vector. What? Long story short. Sometimes when we're trying to put together some of these operations, etc., it might be more useful to think about a vector at its core. That's a weird way of saying it.
You see, put the little arrow on top of the V.
Yeah, can you see it? It's a little bit like, no siento. It's up here. Kind of small. And there's a point divided. So I have vector V in its components. What are his components, guys? Yeah. It's not hard. How far over, how far up, right? And then this one, since it's at 0, 0, it's easy. It's over 7 and up 5, right? Okay. That's our given vector. What are we supposed to be finding in the problem? Unit vector. A unit vector only has a length of 1, right? Length meaning magnitude. So how does that compare to this vector? We know it's supposed to have the exact same direction, so the exact same angle, headed the exact same way. But how can we compare a unit vector which has a magnitude of 1 with this vector which has an over and up of 7 and 5? Sean, what do you think?
Can we use similar triangles?
I like that idea. But to do similar triangles, don't we first have to make a...
Triangle.
Exactly. So let's show our components. Let's show our 7. Let's show our 5. Cool? Let's show our 7. Let's show our 5. Oh, hey. Wait. In order to compare, don't we kind of need to know about V's magnitude?
Yes.
We know about U's magnitude. We need to know about V's magnitude. So hold on, wait. So if we know about V's magnitude, how can we figure out V's magnitude? Remember, double lines, vector V.
You use distance formula.
We could use
What about
distance
Pythagorean
formula.
theorem?
Why not Pythagorean theorem? Because we have over 7 up 5 at a right angle. Ooh.
25, 49.
Over 7 up 5, that's 49 and 25, which is 60, 74. Does that reduce? Not so nicely, 2 and 37. So what do we got?
74.
Okay, cool kids. Algebra 1's been working on this, aka we did a warm-up for about 5 minutes yesterday. You're welcome. What is this number approximately not using a calculator?
Okay, hold on.
Okay,
So 60. So 64 is
12! 12 squared is 144.
8 and
No,
9
2
is
times
1.
37.
So it's like 8.5.
So yeah.
Sure.
It's around 8.5.
Hey, see how close you were. Let's see how good your mental math is.
7.5.
7.5.
8.6.
Ah, 8.6.
I see.
Yeah.
Okay, now hold on. Wait a minute. If this dude is 8-ish, I was going to say 8-ish. He's in between 8 and 9-ish. And what's the magnitude of U?
1, I guess.
Yeah, because unit vector, right? Question, does it make sense to have the unit vector? He's going to be going along the same direction as V, but he's going to be about 1/8 as long? Right? Isn't he about 1/8 as long? Now, I don't want to just say 1/8 as long. That's not very mathematical or precise, and we need to get this unit vector in his component. So question, how do we scale this guy back? How do we go from...
Proportion.
Exactly. How do we scale back, not root 75, sorry, root 74, to be instead square root of 1 if, hold on, you guys, square root of 1, that's lame. That's 1, yeah? Okay, you ready? You ready for this?
Yeah.
Whoa.
Nice.
How do we get his components?
You do 1 over 8.5 equals like.
Because he needs to be
5
1.
over x.
How do we
That's
scale
gonna
back
be
the 5? Yeah, can't we just divide the 5 by square root of 74?
Yes.
Right? Didn't we divide root 74 by root 74 to get 1? Similar triangles, their sides are proportional. So if we divide the hypotenuse by root 74, we gotta divide the opposite by root 74, which means we gotta divide the adjacent by root 74. Remember, cool kids? Whatever, we're getting ready for calculus. Let's not rationalize. Life's too short. But our components will end up being 7 over root 74. 5 over root 74. And if you guys see something like 7 root 74 over 74 in the back of the book, you know they just rationalized, right?
Yeah.
Good talk. Dun dun dun. Now, hold on. We're going to have to keep on going on this section tomorrow, but we are so close to being done. Speaking of unit vectors, I want to give you guys the names of 2 very special ones. Vector I is the unit horizontal vector. He's the special one, the unit vector that is horizontal, going due east. J is the unit vector going due north or going straight up. Put little vectors above I and J. They are not just plain I and just plain J. Their component forms. J goes over 0 up 1. I goes over 1 up 0. Let me show you quickly from up above. There's another way of writing vectors, and they're called linear combinations. Using vector v from above, instead of saying 7, 5 and side carets, we could say 7i, 7 in the horizontal position, plus 5j, because that would take this guy and multiply him by 7, take this guy and multiply him by 5, and we would end up with 2 vectors adding to be a 3rd vector. That's the benefit of this notation. We actually get to make our horizontal vertical pieces into a vector. Can you guys then tell me how would you write, this is called linear combination, stop pause, the unit vector as a linear combination? How would you write them in the same notation?
7 over 74 I plus 5
over 74.
It's as easy as that. Bye guys.
Bye.
If you have not started this homework, a little foolish. If you don't start it by tomorrow, a lot foolish. Come on guys, be amazing. Start your homework tonight.
I will.
And then you want to do this.